Hi, now this session will be on irrational numbers and we'll be focusing on SURDS. So to understand what SURDS are, we have to just cover some keywords to get an understanding on what SURDS are, and then we'll continue on how to simplify SURDS. So some keywords I want you to write down are rational numbers, irrational numbers, SURDS, perfect squares, recurring, and terminating. And some of these might sound familiar, and we'll start with the first one. Or the first two, we'll compare rational numbers and irrational numbers. So basically, rational numbers, in a short version, are numbers that can be turned into fractions. So for example, you might have decimals, and these decimals can actually be turned into fractions, so they're rational. Irrational numbers are the opposite, which means they can't be turned into fractions. And to understand why, with rational numbers, they can be turned into fractions because they have terminating decimals. So terminating means it ends. So another word we use in maths is finite. The decimals are finite, which means the decimals stop at a point. For example, 0.5, it's a decimal, and we know 0.5 is a half as a fraction, and it can be turned into a fraction. And it stops, so the terminating decimal stops. But sometimes we have decimals that don't stop, that don't terminate, and we say they're infinite, going on to infinity and beyond, or never ending. And for example, a third is an example of a decimal that never ends. We get 0.3333 and so on. So when you try and divide this, it never ends. But because it has a recurring pattern or recurring numbers, now recurring, that keyword means repeating, like reoccurring. So you can see that with a third, we've got 0.333 and so on. So 3 is the number in our pattern, and we have a pattern, which is great because now it can be turned into a fraction, even though its decimal never ends. But with irrational numbers, these numbers, they can't be turned into fractions because they have an infinite decimal that has no recurring pattern. There is no pattern that can be found, and therefore they can't be turned into a fraction. For example, examples of irrational numbers are pi. You can think of pi, it's 3.142 and all these other numbers that never end. In our classroom, we have that poster, and you can see a lot of the numbers of pi, but there are many, many, many more because pi never actually ends. And because pi has no pattern, it can't be turned into a fraction. And that's what SURDS are as well. SURDS are irrational numbers that can't be turned into a fraction, but these numbers are different because they have the radical sign. And we know the radical sign, for example, here we have the square root of 3. That root symbol, that symbol here, is actually the radical sign. And with SURDS, the radical sign can never go away. It can't disappear. If you use your calculator, for example, with the square root of 3, we know there is no number times itself twice to give us 3. It's impossible. So there's no whole number, that could be our answer. For example, unlike the square root of 4, we know the square root of 4 is a whole number, 2. And we can see how with the square root of 4, the radical sign disappeared because the answer is simply 2. 2 times 2 gives me 4. But with the square root of 3, we cannot work it out because, like I said, there is no number. That's what a surd is. A surd is a number that has the radical sign that can't disappear. Now, if you put the square root of 3 on your calculator, you'll notice you'll get a decimal, but you'll also notice that your decimal does not end, and there is no pattern. Now, of course, not all the numbers can fit on your calculator screen, so the calculator will stop somewhere at a point or round it off. But if you had a huge poster of the square root of 3, its decimal never ends, and there is no pattern. They're just random numbers that have no pattern. Okay, so just write down these definitions, and it's important that you understand what they mean. Once you've done that, we'll do a quick test to make sure you can understand the difference between rational and irrational numbers, and of course understand what SURDS are. Okay, so with this question here. It asks us to state whether each of the following numbers is a surd or not. So have a go and do these questions yourself and then come back and check to see if you got it correct. So now, the square root of 25. So if it's a surd, then that means the radical sign cannot disappear. Well, I know the square root of 25 is actually equal to 5 because 5 times 5 is 25, and that is my number. So 25, we can say, is not a surd because the radical sign disappeared. Next one, we've got the square root of 20 squared. Now, a trick is if you ever have a squared and a square root together, they actually cancel each other out and you're left with 20. If you wanted to go 20 times 20, because we know 20 squared is saying 20 times 20 to give you 400, the square root of 400 is actually 20. So because the radical sign disappeared, it is not a surd. This one down here, the square root of 5. Is there a number times itself twice to give you 5? No, there isn't. I can't get rid of the radical sign. Therefore, yes, this is a surd. And the last one, now it's not the square root. We can see that power 4 out here. So the 4 root of 100, which is asking us, is there a number times itself 4 times to give us 100? I can't think of a number that can multiply itself 4 times to give us 100. Check on your calculator just to make sure. So we can say, yes, this is also a surd, a surd, because we cannot get rid of that radical sign, and the decimal, if we check in our calculators, it's a never-ending decimal. Okay, have a go at this question first and then just pause it, and I'll go through the answers now. So it asks us to classify each of the following numbers as rational or irrational. Okay, so you should know the difference between rational and irrational. And remember, if you were to study these words in English, irrational, if someone said to you, you're being irrational, it means you're sort of being a bit, I guess, crazy or not really fair. So think of never-ending decimals without a pattern as being crazy. Anyway, so our first one, this should be A, sorry. The A disappeared somehow. We've got 6.222222, and these 3 dots down here are telling us that the 2's never end. Now, yes, the decimal never ends, but it is not irrational because I can see a pattern. I can see 2, 2, 2, 2, 2, 2, and so on. So this number is rational because 6.2222 can be turned into a fraction because there's a pattern in our never-ending decimal. The square root of 8, is there a number times itself 2 times to give us 8? No, there isn't. 2 times 2 is 4. 3 times 3 is 9. I've passed 8. So this is actually a surd. We know it's a surd, and it is irrational. Next one, we have 0.235, and because our decimal actually just stops, it's finite, it ends or terminates, it is rational because we know this can be turned easily into a fraction. And the last one, C, well, you've got a negative half. Straight away we know it's rational because we can see it's a fraction. And it doesn't matter if it's negative or positive, it's automatically rational because it's a fraction. Okay, so now we'll be looking at simplifying surds. And for example, if I have the square root of 8, yes, I know it's a surd. It cannot equal a whole number, but I can make this more simple by simplifying it. Now, before we do this, what I want you to do is to write down the first 20 perfect squares. Now, perfect squares was a keyword, and I'll explain what it is right now. So the first 20 perfect squares, and starting with 1, 1 times 1 gives us 1. So 1 is a perfect square. 2 times 2 equals 4. So 4 is a perfect square. So a perfect square is when 2 numbers that are the same are multiplied together and the products are perfect squares. So basically, next will be 3 times 3, and then 4 times 4, and 5 times 5. Oops, sorry. I'm going a bit too fast. 4 times 4 and 5 times 5. And I'll just stop there because I can't fit any more on my screen. Now, perfect squares are infinite. It never stops. But the first few perfect squares are our only small numbers. So 3 times 3 is 9, 4 times 4 is 16, 5 times 5 is 25. And you notice they start to get larger very, very quickly. So 1, 4, 9, 16, 25, they're special perfect squares because they are the only small perfect squares or small whole numbers that we will see. Because from now on, they'll keep getting larger and larger and larger, and they never stop. So just to point out, and the reason why they're called perfect squares, because we're multiplying the same number. So for example, if I actually drew a square, so if you're familiar with area, then you'll be fine with this. We know a square has 4 perfect sides, which are all equal in length. And therefore, if this length here is just say 2, okay, and if it's a square, we know that this length here is also 2. And then to find the area of this square, I have to go 2 times 2, which will give me 4. Okay, just say in centimeters, so 4 centimeters square, or 4 squares that make up my area. 1, 2, 3, 4, and that's why they're called perfect squares, because all these numbers are being multiplied by the same number, just like a square would be, because a square has to have equal sides. So I have to go 2 times 2 to find the area. And if that confuses you, that's okay, because you have to know a bit about area to understand it. Alright, so now we're going to simplify SURDS by using these perfect squares. And you'll see why they are important. And you can probably see why they are. But let's start with the square root of 8 to work it out. Alright, so sorry, that's our question, the square root of 8. So is there a number times itself twice to give us 8? No, we know there isn't. But what are some factors of 8? Now, when you think of the factors, can you think of one of them being, at least one of them being a perfect square? So one of these numbers. Now, we won't include 1 when simplifying SURDS because we know 1 doesn't change anything. So 1 is excluded when simplifying SURDS, but continue from 1. So try 4, 9, 16, 25. What are some factors of 8 that might be a perfect square? And I know that 4 is a factor of 8, and I know that 4 times 2 is 8. So instead of writing 8, I am now going to write the square root of 4 times 2. Because I know 4 times 2 is still 8. I've just written it in factor form. Now, the next thing I'm going to do is separate the 4 and the 2 into their own square roots. And we can do this when working with SURDS. Okay, so I'm going to just separate the 4 and the 2 to have this. The square root of 4 times the square root of 2 is still the square root of 8. We haven't changed our number. We have now just separated them into their own, under their own radical sign. And now you can see why we did this. Because I know that the square root of 4 is, 2, because 2 times 2 gives us 4. So now what I'm going to do, because I can work out what the square root of 4 is, that is actually 2. So I'm going to have 2 times the square root of 2. Now you notice this square root of 2, it cannot disappear, it can't be simplified, and we know that with SURDS the radical sign can't disappear, and we can see how it's still here. And that is our answer. We have simplified the square root of 8. Now the last thing is that multiplication symbol can become invisible, so we have 2 square root 2. And that would be our final answer. And we have simplified the square root of 8. And we can see how it is more simple because we've got a whole number 2 times the square root of 2, which is a smaller surd and easier to work out. Okay, so let's simplify the square root of 12. So once again, just along here, I've just written down some of my perfect squares just to give me a head start. And I forgot to mention what I want you to do before you continue. Can you please write down the first 20 perfect squares the way I did it before? So 1 times 1 is 1 and 2 times 2 is 2, 2 times 2 is 4, all the way down to 20 times 20, which is 400. So can you please do that and then continue? So now the square root of 12, once again, I have to think of factors of 12 that where one of them is a perfect square. Because, for example, if I said, oh, I know that 6 times 2 is 12, which is correct, and I separated them, so square root of 6 times square root of 2. The problem is, what do I do now? Square root of 6, is there a number times itself twice to give me 6? If I have a look here, no, there isn't. 6 is not a perfect square. I've got 4, 9, 16, and I've passed 6. And the same with 2. Do you see 2 in here somewhere? No, 2 is not a perfect square. So we stop here. We can't continue simplifying, or we really haven't simplified it at all. So I'll cancel that working out, and I'll try and think of other factors. Let's see. I know that the square root of, factors of 12. What about 4 times 3? That also gives me 12. And let's have a look. I'll separate them. So square root of 4 times the square root of 3. And what do you know? The square root of 4 is actually 2. It becomes a whole number 2, and the radical sign disappeared, times the square root of 3. That radical sign is still there. It hasn't gone away. 3 is not a perfect square, so we can't simplify it. But what I can do is have 2 square root of 3. That times is just sitting here, but it's invisible. And that's our final answer. All right, square root of 30. Now, let's think of factors where we have one of them being a perfect square. Well, I know that 15 times 2 is 30. I know that 5 times 6 is 30. 30 times 1 is 30, but we know that the 1 can't change anything. And it looks like that's all I have. Can I use any of these to simplify my SURD? Are any of these numbers perfect squares? No, they're not. And please make sure you've written your first 20 perfect squares and have a look. Is 15 there? No. 2, 6, 5? No. So we can't actually simplify the square root of 30. That is a SURD, and it's in its simplest form. So you can simply say it cannot be simplified. Be simplified. Okay, and that would be your final answer. Okay, so now let's do question 4 and 5. With question 4, you notice there, and 5, there's a whole number now outside the square root of, in this case, 4. Now, what I want to point out is, if I had the square root of 4 by itself, there is actually an invisible 1 just sitting out there, and it's saying 1 times the square root of 4. Just like if we had an x, the invisible number in front of x is really 1, saying 1 times x. So just keep that in mind. So with this one, there is a times in between the 2 and the square root of 4. And if we can simplify our square root of 4, we might have to multiply our whole number that we get with that 2. So for example, I have 2 times. Now for now, what I want you to do is to forget about that 2 times out here and work with your square root of 4. Well, I know the square root of 4 is actually 2, because 2 times 2 gives us 4. 4 is a perfect square. So the square root of 4 is 2. It's not a SURD, so instead of the square root of 4, I'll write a 2. And what is 2 times 2? Because they're both whole numbers, I can work it out. 2 times 2 is 4. And that's our final answer. So with question 5, and I forgot to mention before that we cannot go 3 times 32, even though there's a times there, because that 3 is not under the radical sign. It's a different number. It's a whole number, so we can't go 3 times 32 to give us an answer. But I can simplify the square root of 32, and let's think of some factors where at least one of them is a perfect square. So factors of 32, I know 2 is a factor of 32, I know 4 is. Well, 4 is a perfect square, and 4 times what gives me 32? I know that 4 times 8 gives me 32, so I'll be using that. So, once again, that 3 times stays outside for now, and we have the square root of 4 times 8, which equals, now separate them, so 3 times, and then the square root of 4 times the square root of 8, which equals 3 times the square root of 4 is 2, so that's 2 times the square root of 8, which equals 3 times 2. See how we've got our 2 whole numbers together now? So 3 times 2 is simply 6, times the square root of 8. And we have started simplifying it, but if you have a look, the square root of 8, can it be simplified further? Yes, it can. So the problem with this question is, I said that 4 times 8, yes, it's 32, and 4 is a perfect square, but there was actually a higher factor of 32 that was a perfect square, and that number was actually 16, because 16 times 2 is 32, and if I had have used 16 times 2, I would have gotten my answer straight away, my final answer. But we'll continue with what we have here, and I'll just rub out the top part. And I'll explain what I mean again if it didn't make sense. So I've got the 6 square root of 8 up here now. And the problem is we can't stop here, because the square root of 8, I know, can be simplified further. Because I know that, like before, 4 times 2 is 8. So just keep on going. So 6 times the square root of 8, I know we've got 4 times 2. Once again, separate them. So 6 times the square root of 4 times 2. And then the square root of 4 I know is 2. So finally, I have 6 times 2. Sorry, that should be a square root there. Times the square root of 2. And 6 times 2 is 12. 6 times 2, they're both whole numbers, is 12. Times the square root of 2. And finally, there is my final answer. 12 square root of 2. I can't simplify this anymore. Now, we could have gotten this answer much sooner if we had have used 16 times 2 instead of 4 times 8. But we still got the same answer regardless. But just make sure you don't stop simplifying until you can't simplify anymore. So we'll just quickly use 16 times 2 instead, just to see if we get the same answer. So our original question was 3 square root of 32, and instead of 4 times 8, let's try 16 times 2. So we have equals, so the 3's on the outside, times the square root of 16 times 2. Separate them, so 3 times, funny times, the square root of 16 times the square root of 2. Now, the square root of 16 is a perfect square, and that is 4. The answer is 4. So we know that 4 times 4 is 16. And now we have 3 times 4 times the square root of 2. And what is 3 times 4? 3 times 4, I'll just squeeze it here, is 12. And 12 times the square root of 2. And we know the times becomes invisible. So we still got the same answer in the end. It's just that the first method took us longer because we didn't use the highest perfect square factor of 32. So when doing this, try and think of perfect squares that are factors of the number, but also perfect squares that the larger the factor that's a perfect square, the less working out you need. But it's okay to do it the long way as long as you keep on going until you can't simplify anymore. And for example, if we stopped here, 6 square root of 8, we haven't finished our answer and you won't get full marks because the square root of 8 can be simplified to 2 square root 2, okay? And of course, we had 6 times that. So what I want you to do now is complete the following questions. So you've got 1, 2, 3, 4, 5, and 6. Now with 5 and 6, don't be confused because you see it's in fraction form. All you're going to do is simplify the whole numbers as you would normally with fractions. So for example, I'll give you an example just to start you off if you get stuck on 5 and 6. Just say we had 4 and then the square root of 2, which is a third, over 4. See how the 4 is a whole number on top and then you have a 4 as a whole number on the bottom? The square root of 2 can't be simplified anymore, but our 4 and 4, because they're both whole numbers, one on top, one on the bottom, it's just like having this 4 over 4. Divide them both by 4 and it cancels out to 1 and 1, which equals 1 over 1, which just equals 1. You do the exact same thing here. 4 and 4 cancels out to give you 1 and 1. So you're left with, in this case, 1 times the square root of 2. You'll be left with the square root of 2. So with these, with 5 and 6, treat them as you normally would with fractions. But of course, simplify your SURDS first. Thank you, and I hope that was helpful.